Science and technology in the home of the future. During this series of lectures, I shall be describing to you the impact of new scientific ideas in the home. The influence of electronics, material science, communications is already very, very obvious. There are numerous examples of innovative products that have arisen as a result of a combination of scientific advance on the one hand and market forces on the other. We can truly say that British homes are liberally equipped with labour-saving devices at conservative prices. Behind me here, you see the bridge of technology. What I've tried to convey here is that commercially successful technology arises due to two pressures. We have, on the one side, the scientific push. We have strategic science leading through applied science and technical innovation. On the other hand, equally important, we have trends in society that influence the marketplace. And when these two come together, we have commercially successful technology. Let me give you an example. The one that I want to select is this instrument here, the microwave oven. And let us try and build the bridge for this microwave oven. On the scientific side, some basic research in physics and chemistry, both in electromagnetic radiation theory, in new materials, has given rise to novel ceramic materials and also to magnetrons that provide that microwave power. Equally well, on this side, providing a force, has been this trend towards informal eating arrangements. We have far more working mothers, working wives than we used to. Compared to 20 years ago, people spend 75% less time in the kitchen. And there's this push towards fast food and convenience food. And so as a result, we have a very, very successful product. It's interesting to look into the percentage of items in households. And on the slide here, I shall indicate this. I'm going to examine these appliances, the refrigerator, the colour television, the washing machine, and the video recorder. And we'll see what percentage of homes had them in 1957. You can see that nobody had a video recorder because, of course, they really weren't on the market at that time. But 30 years on, in 1987, what a difference. Virtually every household has a fridge and a colour television, and the large majority as well have a washing machine. It's interesting to bring this slide up to date, and that's what I'll do now. And I'll tell you what percentage of British households have this set of appliances here. On the left, I have a vacuum cleaner. 96% of British homes have a vacuum cleaner. These three items here, the colour television, the washing machine, the telephone, a large, large percentage also have those items. What this means is that if you're going to bring out a new product in this range, if industry is going to bring out a new appliance in that range, there had better be some innovation about it to encourage people to purchase a second one or a replacement. Here I've shown the video recorder. Just in 1 year, that has gone from 40% to 46%. In order to get that higher, one of the big improvements is to improve that man-machine or human-machine interface. You can buy these video recorders now with very clever programming facilities. But do you know, only 20% of the people who buy a video recorder can program them. And out of those 20%, 80% of them do, lying flat on their tummies on the lounge carpet. And so clearly, in order to improve the sales of video recorders, what industry needs to do is to make it easier for that human user interface to be better. These 3 items that I have here, we have double glazing, the microwave oven, and also the home computer, a fair number of homes with all those. Finally, I've got the dishwasher. Only 8% of homes have a dishwasher. And therefore, you don't have to be quite as innovative to bring out a new dishwasher. What industry needs to do in that case is some aggressive marketing to encourage more homes to have a dishwasher. Before going on to demonstrate the new technology that's around, what I want to do now is to give you some essential background theory. In particular, discuss the electromagnetic spectrum with you. You can see behind me the electromagnetic spectrum. On the film here, I've shown it in a bit more detail. This is the part that you're very, very familiar with. This is the visible part of the spectrum. All the colors of the rainbow. We can assign to each one of those colors a wavelength or a frequency. And so, for example, if you take red light, the wavelength is about 0.7 millionths of a meter, or 0.7 micrometers. At the violet end, the wavelength is lower. It's 0.4 micrometers. We can assign, as well as a wavelength, a frequency. To either side of the spectrum here, you have invisible radiation. And so, to the lower end here, we have infrared radiation. All warm bodies, a hot radiator, Gareth Roberts, emit thermal infrared radiation. At lower frequencies still, we have microwave radiation, and then radio frequency at lower frequency still. To the higher end here, ultraviolet rays. You're very familiar with those. They give you sunburn. And beyond that, the very energetic rays, the gamma rays, the cosmic rays. We make far less use of these radiations in the home. It's this end of the spectrum that is all important. If I could have the next slide, please. What I'm trying to indicate here is that this frequency range is very, very important. And many of the appliances we should be talking about are really in this part of the spectrum. Let's blow that up a little. We're talking about the frequency range from 10 to the 6 hertz, 1 megahertz, all the way up to 10 to the power of 10 hertz. Let's take the simple radio, medium band radio. That uses this part of the spectrum. Color television, on the other hand, uses higher frequencies. I've already mentioned to you the microwave oven. This is the band that makes use of. In my lecture today, I shall be referring to radio frequency cooking as well as microwave cooking. We know about visible light, fluorescent light, making use of ultraviolet radiation. In today's lecture, I shall be mentioning radio frequency lighting, and that uses this band here. And finally, on this spectrum, I shall be showing cordless telephones. You've all seen them. We'll be discussing it in a later lecture. That uses this band here. So that's just a selection of the appliances that I shall be discussing. And it is important that you realize that they all have a very characteristic band of frequencies. It is important at the start of every lecture to have a spectacular demonstration. Today, I'm going to concentrate on cooking and on lighting. I have here a very modern two-dimensional fluorescent light. I have here some water. What am I going to do? You've guessed right. I put it in there. Now, what I'm going to do now, please, please don't do this when you get home. Please, please, or your parents will shoot me. I'm going to put it into the microwave oven. And you can see what will happen. Isn't that nice? At the end of this lecture, hopefully you'll be able to understand why that fluorescent light is lighting up as it is. But before that, I want to guide you through the history of lighting and show you where research has gone in terms of modern lighting. Light, or the absence of it after dark, has really had a very important influence in social history. The night cometh when no man can work describes biblically the attitude of people at that time to the hours of darkness. Mind you, Noah in his ark had no problem, of course. He was able to use floodlighting. Behind me here, courtesy of the Science Museum, I have some beautiful examples of lighting from the past. In the early days, we're going right back now to Greek and Roman times, it was a hollow vessel full of oil that was used for the light. So a Roman lamp like this would be full of animal or vegetable oil. The wick would be made of a fibrous plant. So that's a very early example of an oil lamp. Alongside here you see a couple of other examples of oil lamps, and this was the real high-tech version with a special supply, a gravity supply of oil. The oil industry in America in particular developed in about 1860, and that gave quite an impetus to the paraffin oil industry, and these oil lamps developed enormously beyond that time. The Romans were also responsible for introducing the candle. Traditionally, there were two types of wax. There was beeswax, which was rather scarce, and then there was the down-market wax, tallow, made of animal fat. And that tended to smell and really wasn't very easy to use. Just as the oil fields opening up in America helped the paraffin oil industry, they also helped the candle industry because paraffin wax became available and candles were then mechanized. Here's a lovely example of a candle holder from the 18th century. The expression, not fit to hold a candle to anyone, comes from that period, where servants used to follow their masters around, holding the candle and trimming the wick or snuffing the wick as appropriate. A competitor to both the oil lamp and the candle was gaslight. And as early as 1807, the streets of Pall Mall were lit to celebrate King George III's birthday, and they were lit with gaslight. I have here a lovely example of a gaslight. Let me put it on for you. There really is a very bright flame coming from that gaslight. The luminosity comes about because of the carbon particles in the flame. It's the carbon that gets heated up and gives off the light. And as we shall see, carbon is a very, very important ingredient in lighting. Here I've shown a different type of gas light. This is a gas mantle. The principle here is slightly different. In this case, the gas flame heats up a web which is impregnated with certain oxides. And it's those oxides that get heated up and then give off the light. A very special case of a gas mantle is when you heat up this rock here, which is calcium oxide or lime. And Dr. Bryson Gore, who's going to help me with experiments today, is now going to demonstrate to you lime light. And if I could have the lights down and some appropriate music, please. Bryson can illuminate the stage here just as they were a century or so ago. That's lovely, isn't it? Thank you, Bryson. And so gas was really a competitor for oil and the candle. But along came a competitor for gas, and that was electric light. In this lecture theatre in 1808, Sir Humphry Davy, who is very well known for his invention of the miner's safety lamp, demonstrated electric lighting for the first time. What I have behind me here is a very special example of that electric light. And shortly I'll demonstrate it to you. But let me tell you a very surprising fact which I learned researching this lecture. I'm a very keen soccer fan, and I discovered that the very first floodlit soccer match was in Bramall Lane, Sheffield in 1878. The score was 2-0. I'm not sure who was playing who, but each of the teams brought along their own portable steam engines and positioned 4 large carbon arc lamps at each of the corner flags. Isn't that amazing? What I have here is a very special example of the carbon arc. It's called a Japlikov candle. Paul Japlikov was a Russian engineer who was traveling from Moscow to Philadelphia, but stopped in Paris and stayed there. And while he was there, he invented this candle. It's 2 strips of carbon separated by plaster of Paris. And this type of candle was used to light the streets of Paris in 1878. And the Billingsgate Fish Market was illuminated by 16 candles like this. What I shall try and do is to demonstrate it to you. I think before I do some work, Bryson, why don't you take my jacket? Thank you. Now, this experiment doesn't always work. I should forewarn you. Let's see. Well, it's a hint there. It's lovely and bright, isn't it? How about playing football to that? Tremendous. Thank you, Bryson. That type of candle wasn't seriously thought of for home use. It was rather too difficult to control. But there was another type of electric lamp around, the filament lamp, the incandescent bulb. You all have them in the home. Very simple GLS lamps, they're called, General Lighting Service lamps. Many people were involved in the invention of the electric filament lamp. In fact, but for Sir William Crookes' invention of the vacuum pump, they would never have come in the first place. But it's mainly Swan in the northeast of England and Edison in the United States who are classified as the inventors of this electric filament bulb. The principle is very simple. You simply apply a voltage, pass a current through a filament, it heats up. In Edison's case, he used carbonized bamboo as the filament. In Swan's case, he used a carbonized cotton. But carbon is a very, very brittle material, and Coolidge in 1909 discovered that ductile tungsten was a far, far more suitable filament source. And ever since that time, bulbs like the one I've just shown you have a tungsten filament. I have alongside me here a beautiful array of light bulbs, all with different shaped filaments. As you move along here, it's like walking along the streets of Piccadilly. And when you get to the end one here, that's like Soho. It was Langmuir who first suggested the use of a coiled filament to make a bulb more efficient. He also suggested putting an inert gas in there to prevent oxidation of the bulb, of the filament bulb. You see this bulb here. I've selected it deliberately. It's an used bulb, and it has a black coating on the outside. And many of you must have seen that when a bulb is faulty. Let me explain to you now, with the help of the film, just what is happening. This is our bulb, and here's the tungsten filament. We apply some electricity, some power here, and the filament glows. But what that does is to emit tungsten atoms. And these tungsten atoms congregate on the lamp enclosure here. And the hotter this becomes, the darker that becomes. One way of preventing that is to put some bromine, illustrated here by the pink color, a halogen gas like bromine, into the bulb. And what that does is to reverse the process. You get tungsten combining with bromine to give tungsten bromide. And when that happens, the bulb clears. And so most modern bulbs of this kind contain just a few micrograms of bromine. Bryson now is going to try and demonstrate this effect to you. It's a very difficult experiment to demonstrate, but we'll do our best. We've projected onto the screen here, in reflection, the filament of the bulb in that projector. So we have the lamp enclosure here, we have a gas inside, and here's the filament. As he switches the power on, it glows, and nothing happens. And that's because there's some bromine within that bulb. What he's going to do now is to freeze that bromine. He's going to put liquid nitrogen on the stem here and render that bromine ineffective. Now it's cooled down, he's going to repeat the experiment. So now as he heats the bulb up, you should see tungsten atoms coming off, and as you can see, the whole bulb blackens. What we're going to do now is to try and reverse that procedure. He's going to heat up that bromine again using some hot water. While he's doing that, let me just give you a couple of interesting facts about light bulbs like this. I wonder how many bulbs like this is made each year. Can you guess? I'll tell you. It's 10,000 million. 10 to the 10 bulbs like this are manufactured each year. After about 2,000 hours life, these are thrown away and the householder complains. That's very unfair, really, because they cost about the same as daily newspaper, and the householder is quite happy to chuck that away at the end of each day. And yet there's some technology there, and it costs about the same. Another point I want to make to you is that these bulbs are very, very inefficient. Only about 5.8% of the energy you put in comes out. So it's very, very poor value for money. The efficiency of these bulbs, like a 100-watt bulb, used to be measured, believe it or not, in candle powers per horsepower. Isn't that amazing? Now, Bryson, let's see if the bromine has had its effect. Now you see the bulb lighting up, and hopefully you'll see some of the darker patches clearing. Yes, there we are. Well done. I've alluded to the fact that this kind of bulb is very, very inefficient. Why is it that we sell 10 to the 10 of these bulbs per year, when we have fluorescent bulbs that are about 8 or 10 times more efficient? Well, in order to explain that to you, let me go to the slide and describe how a fluorescent light works. I've shown here a cross-section of the fluorescent tube. Inside this tube, there's mercury, and with a voltage, you can produce a mercury discharge. Unfortunately, most of this light that emerges is ultraviolet, and therefore you have to have a phosphor on the outside that converts this ultraviolet radiation to visible radiation. But when you have an efficient phosphor, that's when you get your nice visible light. The phosphor material here is extremely important. And on the next slide, I've indicated to you the typical composition of a phosphor. Most of the phosphor is a halophosphate, a very important phosphor introduced in Britain about 1942. But some expensive blended phosphors are used. And as you can see, they really, really are full of different elements, mainly rare earth elements in the periodic table. And that combination there, which has been carefully optimized by the chemists and material scientists, give very, very efficient conversion from ultraviolet light to visible light. On the stand behind me here, I've a fluorescent tube. Only part of it has been coated, so that this tube here, we should see the nice purple glow due to the mercury. But you can see the contrast here where we have the phosphor. I have here a beautiful example of a very, very early discharge tube. This dates from about 1901, and it's called a Cooper-Hewitt lamp. I have a reservoir of mercury at this end here, and each end of the tube has an electrode. I'm going to apply 400 volts across those electrodes, and by tipping this tube, what we'll be doing is connecting the electrodes with the mercury. You just watch now as the mercury flows from one end of the tube to the other. Here it goes. Now, as I tip the tube, I create a discharge, and there you have it, a mercury discharge. Isn't that lovely? And that's an example dating from way back 1901, well before the fluorescent tube itself was invented. I've described some very complicated blended phosphors to you. However, I have in this box here, and this comes from the archives of the Royal Institution, some natural phosphors, mineral phosphors. And what I'm going to do now is to illuminate them with ultraviolet light. There we are. I'll put them a bit closer perhaps, and you can see how the ultraviolet bulb in here has excited those phosphors. They look like a row of stick of rocks, don't they? Right. So we have these nice fluorescent tubes with efficient phosphors. Why is it that more of these are not sold? Most people just have them in their kitchens. The reason is the electronic ballast. In order to control a fluorescent tube, in order to ignite that discharge to begin with, you need some very, very bulky electrical equipment. This is what hums in your fluorescent fitting. Due to advances in electronics, the size of this bulky ballast has been reduced enormously. I have here a very modern fluorescent light with a very modern ballast. And you can see now how miniature it is. Now you can start doing clever things with that. In another couple of years' time, you'll be able to put most of this ballast on a silicon chip, and then you really will have a miniature ballast. Behind me here, I have a beautiful example of a compact fluorescent light fitting. And just to show that you can really do some clever things with this, how about that for a colourful array of fluorescent tubes? Beautiful. So one advantage of these miniature electronic ballasts is that you can get the size down and then you can use them in the home in much more convenient places. But there's more to it than that. One of the annoying features in the past with fluorescent tubes like this has been that they've flickered. And this is because of 50 hertz mains. And that can give you headaches. But by using this intelligent electronic box, you can avoid flicker by using higher frequencies. Another thing that you can do using the electronics is to dim the fluorescent lights. And so these fluorescent lights, you can see how I can vary the intensity of them electronically. And that's obviously an added feature to have, because now you can save some energy because of that. So the time has come for me to now build another bridge of technology. And I'm going to do it for the fluorescent fitting. So let's build the bridge for the smart fluorescent light fittings. The basic science, novel materials, novel microelectronics work. That has given rise to these nice phosphors that I've described, and smart or intelligent power. Instead of this bulky ballast that I have here, we now have some electronics linked to the light that's intelligent. What does this mean for the marketing people? Well, the interior decorator, the designer, can now go to town. And as I mentioned, you can improve the quality, no flicker, you can control the light, you can dim it, and energy management. If you do a simple calculation, assuming 25 million households, saving 20 watts per bulb, you find that you can dispense with a couple of power stations in this country if everybody converted one of their incandescent lamps to a fluorescent lamp. So that is where lighting is going in the next year or two. But let's think more to the future now. Earlier on, I showed you how a fluorescent light fitting could be stimulated by the microwave radiation. But why not use radio frequency instead to excite the bulbs? And that's what I'm going to demonstrate to you now. This is a very, very new innovation. What I have here is a fluorescent tube, no electrodes at the end, no wires. Here I've got a radio frequency source of power. I'm now going to put this in here. As I say, no wires. And I'm going to switch on. Isn't that remarkable? I've got no wires, and there's that bulb switched on. Just like before, I can dim it. The effect is really quite startling. I'm lowering the power now. See? You can lower the active part of that tube. So you can have a bouncing fluorescent tube. And just to show you I'm not cheating at all, I'm going to lift this out of here. And look, it's still lit. I feel like Darth Vader, I think, holding this thing here. This is my magic sword. So that's radio frequency lighting. That's very much a look to the future. Count Rumford, Sir Benjamin Thompson, was the founder of the Royal Institution. He's very well known for formulating his theories of heat. And he also invented some very, very simple cooking appliances. What I have behind me here are a selection of appliances which have come from various museums in Britain. They're really beautiful. This one here serves as a bridge between lighting and cooking, which is what I'm going to talk about now. This is not a grand lantern. This is an electric fire. And these lamps in here, these are the sausage lamps. There we are. And you warm your hands by them. There's tremendous heat coming out of these lamps. Now, what's this thing here, I wonder? Let me see if I can get somebody to help me. Why don't you with the red sweater come down and help me? Have you an idea what this could be? Look, it's full of lovely filament bulbs.
Cooker?
No, it's not a cooker. Shall I give you a clue? You stay there. I'm going to put it around you. And what it's supposed to help is lumbago. If you've got bad joints, all those filament bulbs heat up, you see.
Awesome.
That's clever, isn't it? Thank you very much indeed. There's no need for me to tell you what this is here, but I bet you wouldn't have guessed without the apple being there. Here's a very early teas made, dating from about 1920, invented by Hawkins. Alongside me here, I've got something which, why don't you with a Newcastle United shirt come down and help me with? Have you seen one of these before?
Is it for drying clothes?
Yes, it is. Good. You're not as young as I thought you were. This is a mangle, and my twin sister and I used to really labour hard to help our mum and dad doing this. Now, why don't you do it? We'll pretend this is full of horrible wet, and you turn it round. That's it. That's it. That's it. And I'll collect it dry on this side. Lovely. And what have we got here, do you think? It's a pair of Arsenal football shorts, I think. Thank you very much for helping. Here I've a very, very old gas stove. Can you imagine the problems involved with cleaning that stove? No wonder that George Bernard Shaw says that the kitchen was the woman's workhouse, if you have to clean a beast like that. In front of me here, though, I have a very modern prototype cooking hob. These are very, very popular because the top is ceramic, very, very easy to clean. Most ceramic hobs like this have under the hob an element full of spiraling metal, just like an electric fire. But this is really a very silly way to cook because we're giving electrical power to this filament here. This then heats up the ceramic. That in turn heats up the saucepan, and that heats up the water. A very, very energy inefficient process. But there's been a quantum change in cooker hob design as a result of the introduction of this type of element. Much the same size, but you'll see it's 4 bulbs. These bulbs actually emerged from the automobile industry. They're tungsten halogen bulbs. That total power is about 1,800 watts. And it's these that are under the cooking hob here. You can see the 4 elements on there. And the big advantage they have is that the ceramic top isn't heated now. The energy goes directly through to the saucepan. So I can put my hand down here without any problem at all. These have taken considerable development work to reach this stage. A lot of power is there, and so the material underneath here has had to be developed to reflect heat. And it's a space shuttle type tile material that is used. These lamps originally were not too robust, but they've been made very robust now, so if somebody dropped a big saucepan, they'd still survive. But one of the key features has been developing a ceramic which will allow that heat radiation to be transmitted. I can show you the principle here very easily. I have a bulb. The intensity of the radiation is being picked up by this emitter here. I have two pieces of ceramic. This is the ceramic from the normal cooking hob. If I put that in the beam of the bulb, you see it kills virtually all that heat radiation. But this is the specially developed ceramic. And now if I put that in the beam, about 60% or more of the light is transmitted. And so this is the new ceramic that has been developed specifically for this cooking hob. That type of cooking by light principle is also used in this oven here. And so within this oven here, there's the microwave power that cooks the food, and also the infrared heat that gives you that wholesome brown appearance to cooked food. Microwave ovens like this are very, very safe. Microwave radiation doesn't escape very easily from an oven. You might say, well, why is it safe if we have a door that we can see through? This is a special door that doesn't allow microwaves to come out, and yet allows visible radiation through the other way. To explain how this works, I have a very simple demonstration here, and the subject of physics I'm dealing with here is polarization, as some of you may have done in school. I want you to pretend that this snake is an electromagnetic wave. So it's propagating in this direction here. Electromagnetic waves have two parts to them. There's an electric field and there's a magnetic field, both at right angles to the direction of propagation. If the beam is polarized in this direction, as you can see, it can easily get through this gate. On the other hand, if it was polarized in this direction, it couldn't. If I want to make sure that it doesn't get through at all, then if I just have one gate at right angles to the other, then no matter which way I try, that wave won't be transmitted. What I want to demonstrate to you now is this microwave equipment here, and use it to show that microwaves are polarized and why it is that that oven is very safe. If I could have a young lady to help me with this, would you like to come down and help? What's your name? Fiona. Have you seen one of these before, Fiona? You can guess what it is, can you? It's a comb. And we're going to pretend that that comb is a gate. So if you come and stand here, and if you hold the comb, what we have is a source of microwave power, and on the instrument here, we can find out how much power is getting to the other side. What I want you to do, first of all, is to put in the comb in that direction, and we'll see whether that has any effect on the microwaves. That's right, put it in the beam. It's had no effect at all. On the other hand, I want you now to turn it around this way, that's it, and it's had a colossal effect. It really has helped to cut down the microwave radiation. And here I have an oven door, and can you see it's a lovely mesh? And so really it's a combination of the wires like this and like that. And now you put that oven door inside. And that's effectively killed all the radiation, and that's why it is the microwave oven is so safe. But why not have that as a souvenir for helping me? Thank you very much. Well, having extolled the virtues of microwave cooking, why don't we think about its limitations? I want to tell you now about a competitor to the microwave oven. And to do that, I want to use the slides. Here we have, again, the electromagnetic spectrum. We have the microwave region here, the radio frequencies lower down. On the next slide, I've indicated the range where I shall be talking about in terms of cooking. 10 to the 9 is approximately the band where we have microwave cooking. Now I want to talk about a revolutionary type cooker that cooks using radio frequencies. So here's the microwave, and at much lower frequencies, we have my radio frequency cooker. There are about 2 orders of magnitude difference in the frequency that I shall be using. So this is about 14 megahertz, and this will be 2,450 megahertz. Now, how does a microwave oven cook? Well, if I can have the next slide, this indicates water molecules. If you apply microwave radiation to the water molecules, they rotate and they agitate and they heat up the food. So it's the water content in food that is stimulated by the microwave radiation. If we now forget about microwaves, here we are back with our distilled water. If we apply radio frequency waves, which are much lower in frequency, nothing happens. Radio frequencies don't influence water at all. What they do influence, however, is ions. And so if we add some salt to the water, and now we apply the radio frequency, we do get the agitation, and we can get cooking again. And so microwave cooking is very different to cooking with radio waves. There's another very, very important difference too. There's our turkey roast. Let's suppose you put it in a microwave oven. The microwave radiation only penetrates about 1 centimeter into that turkey. And so to heat up the center of the turkey, you have to rely on conduction, which is a very slow process, to gradually heat up this region here. On the other hand, with my novel radio frequency oven, we can start again with the turkey. The radio frequency has a penetration depth about 10 times more than the microwave radiation, and so it penetrates the whole turkey, and you get uniform cooking. So that's a tremendous advantage compared with a microwave. Now, to complete the lecture, we're going to have some fun. And we're going to do some cooking. And so, Bryson, you can be Delia Smith. We're going to cook a turkey roast. I would far prefer to have cooked a Welsh lamb roast for you, but because it's close to Christmas, you can see that in this oven here, I have a turkey roast, and there's an identical one in here. And Bryson and I are going to switch on these simultaneously. I'll say 3, 2, 1, go, shall I? 3, 2, make sure he doesn't cheat. 1, go. Right. So we now have our turkey roast being cooked in a microwave oven and in a radio frequency oven. While that's happening, let me show you a couple of things. Here's the turkey roast. Many of you will have measured resistances, capacitances in school as part of your physics lessons. But how many of you ever measured the resistance of a turkey roast? Or a cake mix? But it really is important to work out the impedance of something like this before you put it into a radio frequency oven. Let me see what it is. 11.1 ohms. That's some useless information for you. The resistance of a turkey roast. Another important feature that I want to demonstrate to you is the importance of salt for radio frequency cooking. And perhaps I could have an assistant here. Would you like to help me? What's your name?
Anna.
Anna. Come on, Anna. Come see if you can do some cooking with me. What I want you to do is to pour this water. Why don't you come around here? You'll find it easier. Can you pour that water into this container here? Right. Now, what I want you to do is to tip this salt and put it into this beaker. And give it a good stir. That's excellent. Once more for luck. Right. And will you pour that into here? Good. Now, the reason I've asked you to do that is that I have two light bulbs here. Now, if that water is resistant, that circuit isn't complete and the light bulb won't come on. On the other hand, if this is conducting, the light bulb should come on. So, Bryson, if you can switch on the power, you see, it proves that the water and the salt is conducting.
Yeah.
But some of the people in the audience will say I've cheated and I've put in a dummy bulb in there. So I want you to prove that they're wrong. And what I want to do now is to pour some of the salt water into this container here.
Yeah.
Oh, you'd already filled it up too much. There's not enough. Let's see if I can make a mess at the same time. It's come on. See, I wasn't cheating after all. Welshmen don't cheat. Thank you very much indeed. So in this lecture, I've shown you cooking, lighting, right from the distant past all the way through. RF has been the answer for lighting. Has it been the answer for cooking? Well, let's see. What I've got here is a very special thermometer. These fiber optic probes here, one has gone into the heart of the turkey roast in here, and the other has gone into the turkey roast in the oven here. And what we want to do now is to measure the temperature. And on the screen, I hope you can see that the microwave roast, at the center, it's only about 21 degrees. It's hardly heated up at all. Whereas the radio frequency roast is already up to 66.2 degrees. And that's already cooking. And so it really has proved that the penetration depth, the speed of cooking with a radio frequency oven is far, far better. Well, it has been defined that a professor is somebody who talks through somebody else's sleep. I hope that hasn't been the case today, and that you'll be able to join me in the next lecture in the scientific pantomime. Tomorrow's lecture will concern safety in the home security, the safety of buildings. I've called it Home, Safe Home. I hope you'll join me then. In the meantime, there's a lovely smell coming from here, from my radio frequency oven, and I'm going to eat my dinner. Thank you.